In this lecture of organic photochemistry, we will discuss about the Jablonski diagrams, which represents the energy of various levels. Like this represent the energy. So this is your singlet ground state S0. This is a singlet excited state S1. This is triplet excited state. Last lecture we discussed that the triplet states have lower energy than the singlet state. So there are various types of transitions possible when the electron is present over here and it is radiated with some radiation. So it go to singlet S1. Then from here the electron come back by various pathways. It may come directly from S1 to S0. Now it will come back through various pathways. Means it may come directly from S1 to S0 by emitting a radiation. Okay, and second possibility is it may move to S1 to S0 by internal conversion by emitting heat. Okay, energy is emitted in the form of heat. It may move from S1 to T1. This is called ISC, intersystem crossing. Okay, and from here it may come directly to the ground state by emitting a radiation, or it may move to this ground state by emitting a heat. So these are the various transitions. This is for n-pi star transition, and when the electron is present in S0, means ground state, when it is radiated or destroyed with some photon, it moves to S1. From S1 it moves back to ground state by various pathways. These are the various pathways. Now we will write their names, specific names. Like from first of all this S1 to S0 means ground state by emitting light. Okay, so this process is called fluorescence. This process is called fluorescence. Clear? Energy is emitted in the form of radiation. Then next is S1 to S0 by emitting heat. This triangle that represents heat. So second step is S1 to S0 by emitting heat. This is called internal conversion. Internal conversion. We can write it IC. Okay. Third is this S1 electron may jump from S1 to this T1. Okay, so we can write it S1 to T1. When it moves from S1 to T1, it emits radiation in the form of light, H nu, and this process is called ISC, internal intersystem crossing. This is intersystem crossing, ISC. Okay. Two more transitions are the T1 to S0 by this emitting light, and T1 to S0 by emitting heat. So when it emits heats, that is called the same internal conversion. And when it emits light, in this case, that is called the phosphorescence. The process is known as phosphorescence. So these are the various types of transitions. So these various transitions like phosphorescence, internal conversion, ISC, intersystem crossing, phosphorescence. Some are transitions that emit light, some emits you can say heat. So these transition, they takes different times to happen. So how we can compare? We must take do not need to memorize, but once we take these numbers in the form of numbers, okay, how much time it will take from the particular transition to take place. Like this is your fluorescence. I will write it F. Okay, this is from S1 to S0. So the time for this is, so you can say Kf. F means first fluorescence. That is about 10 is per 5 to 10 is per 6 seconds. 6 per second. Okay, this is the rate constant for this. And this is your internal conversion. The time period is for 10 is per 15 or 14 seconds inverse. It's faster. This transition, intersystem crossing, that takes 10 is per 8 to 10 is per 10, okay, not 12 per second. This is your fast fluorescence P. So this Kp is equal to your 10 is per 2 to 10 is per 3 per second. And again you have this interconversion that takes 10 is per 14 per second. So these are the some values of rate constant, how fast the transition take place. Okay, and now we can compare like 10 is per 5, 6, 10 is per 2, 3. It means fast fluorescence is faster than the that of your fluorescence. So when one electron is radiated from ground state, now in photochemistry, what is given there is a single compound, reactant, the R. That we have to radiate that reactant with a particular wavelength of radiation. When we radiate, the electron jump from S0 to S0 to S1. And from S1 is the singlet excited state. From here, from S1 it may go to T1. If the energy gap between S1 and T1 is less, it may go to T1. Then after the electron reaches to T1, it will come back to the ground state. So where the reaction takes place actually, and in the photochemical reaction, what we have studied is that R changes to R dash. What is the meaning of R dash? R dash means it's excited state. R is in the ground state, R going to the excited state. Okay, so when we radiate any particular substance, that first go to the excited state. After that, it may change to some intermediate. After that, changes to product. So these are the steps. Suppose R is here, we radiate, it go to singlet state. It may come back by the same way, or it may, when it is reached here, its energy is more. What it can do electron transfer, it can do atom transfer, it can do some bond breaking, some bond making, and ultimately it changes to I, intermediate. Intermediate is a ground state, that is a highly unstable species. That immediately change into product. Either we have a R star here, that R star may change into triplet state, like R change into R star singlet, change into R star triplet, then it change into I, then it change into product. That is also possible. So that depends upon the energy gap between the so you can also write it like R, okay, R star S1, R star T1. First it reaches to singlet S1, then it by undergoing this ISC, it changes to R star T1, that it ultimately give to I, then give to P. So we expanded the mechanism little bit more. Okay. Now any compound which is given, we are here, when it radiated, it reached to S1, it may change to T1, then it may give I, and then give the product. Okay. Now there is one more question, that while studying these Jablonski diagrams, we generally ignore S2, S3, S4. So there are not only two energy levels like S1, S2, there is also S2, there is also S3, there is also S4. But we generally take S1. Why we take only S0 to S1, not S0 to S2? We never consider these transitions. So we try to find the reason. What is the reason? Is that we generally take this transition and we never take S0 to S2, S0 to S3. Question is why? Now the answer is that S2, S3 and S4 vibrations, they collapse. In photochemistry, these S2, S3 and S4 vibrational levels, they collapse. Vibrational levels, they collapse. Okay, so they collapse only, they want to get only S1. To get only S1 state. So when you take S1 state, this rule is called a Kasha's rule.